All right, we're looking at more questions from section 3.1. 54 says at what point on the curve y equals 1 plus 2 e to the x minus 3x is the tangent line parallel to the line 3x minus y equals 5. And then they want you to take a look at it. You can use Desmos afterward to do that. Notice the question is saying at what point. So our answer to this question is a point. And so we got to write x and y coordinates for that point to answer the questions completely. So, you have to remember from a previous class what it means for lines to be parallel to each other. When lines are parallel, they have the same slope. So if we're going to want a line parallel to this line over here, we ought to find um, the slope of this line. So if we go through and we solve for y, then we see that we have a slope of 3, okay? And so we want the tangent line to this curve at some point to have a slope of 3. And so if I take a look at the derivative 1 is 0. Derivative 2e to the x is just 2e to the x minus 3. And so there's the derivative. I need a slope of 3, so I'm going to set the derivative equal to 3. So I can start to solve. So 2e to the x is going to equal to 6. Yeah, I'm just double checking over my shoulder there. E to the x is going to be equal to 3. And then you should take the natural log of both sides to get natural log of 3. And then you just got to find the y coordinate that goes with that. So you're going to want to plug that back in up there to get the y coordinate and then go illustrate it by looking at the graph. Next, we're going to look at number 56. Where does the normal line? Again, we said this, I said this in the previous video. So if you watch the previous video, you'll know what the normal line is. But if you didn't, you should go look it up. So you shouldn't be waiting to always ask for help when you have, the internet or just the textbook to go, um, do a quick little search. It won't take you that long to find it. But the normal line is perpendicular to the tangent line at the point of tangency. And so, we need the slope of the tangent line, and then we'll just take its opposite reciprocal, get the slope of the normal line. So the parabola is y equals x minus x squared. I didn't even read the question, so hold on. I got to go back and read the question. Something about a normal line. Where does the normal line to this parabola at the point 1, 0 intersect the parabola a second time? So this one here, I'm going to give you just a quick sketch of it. I don't know what the graph exactly looks like. It goes through the origin, it's concave down. I think it's on this side of the axis over here, but I'm not 100% sure. And if I'm wrong, oh well. It looks, it says at 1, 0. So so my scale is way off over here. So this must be 1, 0 way over here because it goes through 0, 0. Now, if you imagine a tangent line to the curve right over here at 1, 0, and then the normal line, which is perpendicular to it, going over here, it's going to intersect the curve a second time. This is what we're trying to find. We're trying to find that point. So most of the algebra here is just that. It's just algebra from a previous class. So if you take the derivative, you get 1 minus 2x. You're going to plug in, since the normal line is at the point 1, 0, you're going to plug in 1 for x over here to get the slope of the tangent line. Then you're going to get the slope of the normal line, okay, which is the opposite reciprocal. Write the equation of the normal line. You'll have the slope, you'll have the point, and then it's just a matter of solving the system of equations. You're going to use this equation here and the equation of your normal line to solve the system. And then one of your points of intersection will be 1, 0. That's not the one we're interested in. We want the other one. So it's just algebra at that point. So go work on that algebra. 58 is next. It says find equations of both lines through the point 2, -3 that are tangent to the parabola y equals x squared plus x. Show that there is no line through the point 2, 7 that is tangent to the parabola, then draw the diagram to see why. So we did examples like that, an example like this in our notes. The The point it went through was 0, 11, I think. I don't remember the example number. And it's going to go through the point. The tangent lines have to go through 2, -3. So if I take the derivative, and then we write the equation of the tangent line in terms of a being the x-coordinate of the point of tangency, like this. 2 in this 2, 3 point, -3 is not a. Okay, that's not the point of tangency. 2, 3 is not even on the curve. If you plug 2 in here, 2 squared is 4, plus 2 is 6. So this point is not on the curve. Okay, so you can't plug 2 into the derivative to get the slope. What we do is we're going to write the equation of the tangent line, and we did this in our notes. We're going to write it in terms of a, because I don't know what a is. So f prime of a, plug in a here, f of a, plug in a here. And then we're going to solve for a, but I need to get rid of the x and the y. I know it goes through this point over here, so I'm going to plug in -3 for y, and we're going to plug in 2 for x. And then you're going to solve that for a. When you solve that for a, that's not the answer to the question, okay? Let's go back for a moment. It says find equations of both tangent lines, okay? When you find the two values of a that you're going to get when you solve this, I'm going to write it like this: a sub 1 and a sub 2, because you're going to get two of them. Okay, go calculate the y coordinate of the point by plugging it back in here. Okay, no, don't do that. What am I talking? Yeah, that's fine. I'm sorry. That is correct. Yes, go find the y coordinate of the point, plugging it in here. Then go find the slope at each of those. And then you'll have your slope, you'll have your point, you'll have your other slope, and you'll have your other point. Go write your equations of the tangent lines. Now, the second part of the question for part B, when we go back to this right over here, and the other point is 2, 7, so you're going to plug 7 in for y, and again, 2 in for x. When you solve this, there should be no real solution. I'm not going to do the work for you, okay? This is just a quadratic, and that should be 2 minus a right there. Just do the work. Go to solve it. You might have to use the quadratic formula, and then show that you don't get a real solution, and so that's why this doesn't go through. There are no tangent lines to this curve that go through that point. You can go to Desmos and graph it and see maybe a little bit more why that's true. All right, let's keep this going here. 61 is next on the list. Find a second degree polynomial p such that p of 2 is 5. I better start taking notes here. P prime of 2 is equal to 3, and P double prime of 2 is equal to 2. A second degree polynomial looks like this. P of x is going to be equal to a x squared plus bx plus c. And you need to find a, b, and c. And basically, it's just going through and setting up relationships based on these three points they give you up here. So I need the derivative. I need the second derivative. All right, so let's start with the p double prime equation there. P double prime of 2 is equal to 2, but there's no place to put the x. So 2 is going to be equal to just a 2a, okay? Because you don't plug it in for a. A is not x, okay? So now solve for a. And then p double prime, I'm sorry, that we just used p double prime. P prime of 2 is this one here, that's 3. So I'm going to plug 2 in for x here. We're going to get 4a plus b, but you just found what a is equal to here. Plug that in, solve for b. And then do the same thing with p of 2 is equal to 5. I'll let you do the rest. You're going to plug 5 in for x here. You're going to plug in your a's and your b's, and you're going to solve for c. 62. This is a good preview of something we're going to be doing late in the year, close to the AP exam. we're going to be learning about these things called differential equations. And so it says the equation y double prime plus y prime minus 2y is equal to x squared is a differential equation. Y double prime plus y prime minus 2y is equal to, was it x squared? Yeah. Because it involves an unknown function y and its derivatives y prime and y double prime. Find the constants a, b, and c such that the function y equals ax squared plus bx plus c satisfies the differential equation. And they tell you we're going to learn about those in chapter 7. So what we're going to do is we're going to take the derivative, plug it in here, take the second derivative, plug it in here, plug y in here, and then do some algebra. So the derivative is 2ax plus b. That's horrible. The second derivative is equal to 2a. All right, so y double prime is 2a plus y prime, 2ax plus b, minus 2y, ax squared plus bx plus c, and that has to equal x squared. But I'm going to be a little bit more clear, plus 0x plus 0. You'll see why I'm doing that in just a moment. All right, I got some x squared terms and some x terms here. I'm going to do some of the algebra, and I'm going to gather all those like terms together. So minus 2ax squared minus 2bx minus 2c. So we only have one x squared term. That still equals all this stuff over here. Sorry for being lazy. So we got our 2ax squared term. I'm going to put that out in front. Now we have two x terms. We have this x term right here, and we have this x term right here. So if I put those together and factor out the x, so it's going to be plus, and I'm going to factor out the x. I'm going to have 2a minus 2b. And then all of these other terms that are left that I haven't used yet, the 2a, the b, minus 2c right over here, all of those are the constants. Okay, so I'm going to keep those all together at the end over here. So plus 2a plus b minus 2c. And we want this to be true for all values of x. We want this to be an identity. So that means whatever's on my left-hand side of the equal sign here has to be identical to the right-hand side, not just at some one or two values of x, but for all x, which means they have to have the same coefficients. So the 1, that's a coefficient on x squared over here, also has to be the same thing as the negative 2a over here. So that means negative 2a has to be equal to 1 if the left side is going to be equal to the right side. Same thing here, the 0 in front of the x has to be the same thing as 2a minus 2b. And then the 0, that's the constant, has to be this stuff over here. So 2a plus b minus 2c has to be equal to 0. So solve that first one for a, plug it in to find b, plug a and b in over here to find c. All right, 66 is next on the list. Suppose the curve y equals x to the fourth plus ax cubed plus bx squared plus cx plus d has a tangent line when x equals 0 with the equation y equals 2x plus 1, and a tangent line when x equals 1, y equals 2 minus 3x. Find the values of a, b, c, and d. All right. So let's take the derivative first before I record that other info that we have. Derivative of d is 0 because it's a constant. Now they tell us that tangent line when x equals 0 is 2x plus 1. So that means y prime, when I plug in 0, is going to be 2. Y prime, the derivative at 0, is going to be the slope of this tangent line. If that's the tangent line, its slope is the value of the derivative at 0. So 2 is what y prime is. So if I plug 0 in for x here, actually, let me just do this. If I plug 0 in for all these x's, I'm going to get c is 2. So I already found c. They also told me that y, the tangent line when x equals 1 is 2 minus 3x. So negative 3 is the slope of that line. So y prime of 1 is equal to negative 3. This is going to take a little bit more work. So if I plug in 1 here, we're going to get 4 plus 3a plus 2b plus c. But c we now know is 2, so might as well plug it in there. All right, I have that. We have 3 more unknowns, A, B, and D. We need 3 equations to find the 3 unknowns. And so I'm going to use one other fact. The tangent lines intersect the curve at the point of tangency. So at x equals 0, if the tangent line is y equals 2x plus 1, I think I'm remembering that correctly, then if I plug in 0 for x, then the point 0, 1 is on the curve. Okay, let me repeat that. If you look at a tangent line, let's say this is the curve. This is not the curve, but just to give you an illustration for just a moment. If I look where the tangent line intersects the curve, let's say I missed. Let's say it intersects right there. They both go through that point, okay? The y-coordinate, the x-coordinate and y-coordinate of that of the curve is the same as the x-coordinate and y-coordinate of the tangent line. So if the tangent line goes to the point 0, 1, so does the curve. So that means if I plug in 0 in for y of 0, I have to get 1, which is nice because that means all of these terms here become 0 and I'm left with d. So now we know d is 1. What else? All right, so at x equals 1, we had y is equal to, was it 2 minus 3x? Yeah, 2 minus 3x. So what point goes for that? If I plug 1 in for x, I get 2 minus 3, which is negative 1. And so that means if I plug 1 in to the original equation, the output's got to be negative 1. And so I'm plugging in 1, so it's going to give me 1 plus a plus b. Now c we know is 2, d we know is 1. And so now we need one more relationship to figure out a and b. Let me go back and look at the problem here. Oh, we got this equation up here. This is what I'm forgetting. Between this equation and, whoops, went a little short on my box there. And this equation right here, you're going to solve that system for A and B. Forgot we had that equation. So simplify, solve for A, solve for B. That's just algebra at that point. One more problem, number 71, and then we'll be done with this homework assignment. Number 71 says to evaluate the limit as x approaches 1, x to the 1,000, if I'm reading that correctly, yeah, 3 zeros, minus 1 over x minus 1. They do not want you to try to do this using the limit properties that we learned in chapter 2. They want you to do this using what we understand this expression represents. This should look familiar. We had this expression, the limit as x approaches a of f of x minus f of a over x minus a. That's the derivative. This is f prime of a. I taught you guys this back in section 2.6 and again in 2.7. We don't use this form of it as much as we use the one where h approaches 0, but this is the derivative. So all we need to do is tell or look at this and understand what function we're taking the derivative of and where we're taking it, and then apply the shortcuts that we've learned here in section 3.1. The function here, well, f of x is right there. It's x to the 1,000. And then we need to find, this says x approaches a, so we're finding f prime of 1. So go find f prime of x using the power rule and then plug in 1. All right, ladies and gentlemen, go study.